Hello there, and welcome to another Google Hangout for AMP2. I'm covering Chapter 15 today, the cardiovascular system. Apparently, my desktop's time is 2 hours ahead, or I'm sorry, behind, and the notification I sent out about this broadcast is showing that it's not going to start for another 2 hours, but we are starting it in a couple minutes as soon as I pull up the PowerPoint. Introduction to the cardiovascular system. The heart pumps 7,000 liters of blood through the body each day, contracting some 2.5 billion times in an average lifetime. The blood vessels form two circuits. The pulmonary circuit sends oxygen-rich or poor blood to the lungs to pick up oxygen, unload carbon dioxide. The systemic circuit sends oxygen-rich blood and nutrients to all body cells and remove waste. Without this circulation, tissues would lack a supply of oxygen and nutrients, and waste would accumulate. Such deprived cells would soon begin irreversible change, which would quickly lead to their death. This next slide shows how the systemic circuit works and how the pulmonary circuit works. The systemic circuit delivers oxygen to all body cells and carries away the waste. The oxygenated blood returns to the heart via the superior and inferior vena cava. It travels into the right atrium and flows through the tricuspid valve to the right ventricle and is then pumped through the pulmonary semilunar valve to the pulmonary arteries to the lungs, where oxygen is given into the blood and CO2 is taken out of the blood, and your lungs exhale the CO2. The oxygenated blood then returns to the heart via the pulmonary veins, travels through the left atrium, through the mitral valve to the left ventricle, through the aortic semilunar valve to the aortic arch, and then onto the aorta, and it's pumped to all the body tissues. Slide 15.2 shows the structure of the heart. It's hollow, cone-shaped. It's a muscular pump with 4 chambers, 2 atria for blood storage, 2 ventricles. One is a low-pressure pump and one is a high-pressure pump. A few facts about the size and location of the heart. Heart size varies with the body size. The heart lies in the thoracic cavity. The average size is 14 centimeters long and 9 centimeters wide. It lies posterior to the sternum, medial to the lungs, anterior to the vertebral column. The base lies beneath the second rib, and the apex is at the 5th intercostal space. It lays just above the diaphragm. This slide shows a more illustrated picture of that. The coverings of the heart include fibrous pericardium, and there's also a visceral pericardium and parietal pericardium. The visceral pericardium is actually the same as the epicardium. So the epicardium makes up the outer layer. The myocardium is the middle layer, which is the heart muscle itself, and the endocardium is the inner layer. And this table 15.1 Shows the function of each of the layers. The epicardium forms a protective outer covering. It also secretes serous fluid. Between that and the other layer, the parietal pericardium, the myocardium contracts to pump blood from the heart chambers, and the endocardium forms a protective inner lining of the chambers and the valves. Heart has 4 chambers. The right atrium receives blood from the inferior or superior vena cava and the coronary sinus. The right ventricle receives blood from the right atrium. The left atrium receives blood from the pulmonary veins, and the left ventricle receives blood from the left atrium. Table 15.2 shows the valves of the heart and where they're located and their function. The tricuspid valve is located in the right atrioventricular orifice. It prevents blood from moving from the right ventricle back into the right atrium during contraction. The pulmonary valve is at the entrance to the pulmonary trunk. It prevents blood from moving from the pulmonary trunk back into the right ventricle during ventricular relaxation. The mitral valve is located at the left atrioventricular orifice. It prevents blood from moving from the left ventricle back into the left atrium during ventricular contraction. And the aortic valve at the entrance to the aorta prevents blood from moving from the aorta back into the left ventricle during ventricular relaxation. This slide shows a cross-section of the heart and the valves and the blood vessels that serve to promote circulation through the heart. You can see a superior vena cava, a pulmonary valve leading to the pulmonary trunk, and then we have the aorta here. These are left pulmonary veins that feed into the left atrium. These are the right pulmonary veins from the right lung. And there's a picture of the tricuspid valve on the right side and the bicuspid valve on the left side. And here's another slide of the right atrium, the cusp of the tricuspid valve, the chordae tendineae, that's part of, attached to the heart muscle. Here's an interventricular septum and some papillary muscles and some muscular ridges. The skeleton of the heart is the fibrous rings that come together in the portion of the septum between the ventricles, and that constitutes the skeleton. So it's kind of encased, everything's encased in the skeleton, the valves and the openings to the artery. Here's how the path of the blood flows through the heart. In the tissue cells, CO2, oxygen is taken in, CO2 is given off. That blood that's deoxygenated with low CO2 travels to the right atrium, to the tricuspid valve, into the right ventricle, through the pulmonary valve, to the pulmonary trunk, to each separate pulmonary artery, the left and right, and then in the lungs, in the alveolar capillaries, there's a gas exchange again. CO2 is blown off, and oxygen is taken in, and now we have oxygenated blood that travels into the left atrium, goes through the mitral valve into the left ventricle, and is pumped through the aortic valve into the aortic arch, and either travels up the ascending aorta or the descending aorta. And then again, the process goes through again. The gas exchange occurs. Oxygen is used up by the cells. Some CO2 is given off, and then the process begins again. And here's just a flow chart of that. As you can see, the right atrium, blood travels through the tricuspid valve, the right ventricle, to the pulmonary valve, to the pulmonary trunk, to the pulmonary arteries, into the lungs. Gas exchange occurs in the alveolar capillaries. The oxygenated blood is then sent to the pulmonary veins, to the left atrium, through the mitral valve to the left ventricle. It's pumped through the aortic valve to the aorta and back to the systemic circuit. This slide shows the blood supply to the heart. The left and right coronary arteries supply blood to the tissues of the heart. So the aorta branches to the right coronary artery and left coronary artery. The right coronary artery has two branches, a posterior interventricular artery and a marginal artery. The posterior interventricular artery sends blood to the myocardial capillaries and the ventricular walls. The marginal artery sends blood to the myocardial capillaries in the walls of the right atrium and right ventricle. While at the same time, the left coronary artery divides into the circumflex and the anterior interventricular artery. The circumflex artery sends blood to myocardial capillaries in the walls of the left atrium and left ventricle, while the anterior interventricular artery sends blood to the myocardial capillaries in the ventricular walls. All that blood is then pumped to the cardiac veins through the coronary sinus to the right atrium. And here's a dissection of the aorta, showing the aortic valve and the three cusps, and showing the opening of the left coronary artery and the right coronary artery is right there. There's the opening. And this is some of the structures that we normally see in the heart. As you can see, these veins and arteries travel pretty much through the apex of the heart. The heart chambers function in a coordinating fashion. Heart actions are regulated so that the atria contract, which is called atrial systole, while the ventricles relax, which is called ventricular diastole. And that's followed by the ventricles contracting, or ventricular systole, while the atria relax, atrial diastole. So while ventricles relax, the atrials have to contract to pump blood into them. And then when the ventricles contract to pump blood out, the atria relax. So valves must close for this in order for this to happen. When the tricuspid and mitral valves open, blood flows from atria to ventricles. And then the pulmonary valves and aortic valves are closed because we have diastole in the ventricles and we have systole in the atria. So contraction of the atria, we must have relaxation of the ventricles. There must be higher pressure in one and lower pressure in the other. And then when the ventricles contract, the enter systole, both the aortic and the pulmonary valves open, while the tricuspid and mitral valves close to prevent the backwash. And while this ventricular systole or contraction is occurring, the atria must relax, and they must stop pumping blood into the ventricles. So in order for too much blood, otherwise we'd have too much blood flowing in the ventricles. During a cardiac cycle, the pressure in the heart chamber rises and falls. In atrial systole and ventricular diastole, the blood flows passively into ventricles. The remaining 30% of the blood is then pushed into the ventricles. The AV valves open and those semilunar valves close. The ventricles are relaxed. This causes an increase in ventricular pressure. And then in ventricular systole and atrial diastole, the AV valves close while the chordae tenonate prevents the cusp of the valves from bulging too far into the atria. The atria are relaxed, blood flows into the atria, the ventricular pressure increases and opens those semilunar valves, and the blood flows into the pulmonary trunk and aorta. And here's an animation of the cardiac cycle.
Ventricular contraction causes the atrioventricular valves to close, which signals the beginning of ventricular systole. The semilunar valves were closed during the previous diastole and remain closed during this period. Continued ventricular contraction increases pressure in the ventricles above the pressure in the aorta and pulmonary trunk, causing the semilunar valves to open. When the ventricles relax and their pressures drop, blood flowing back toward the relaxed ventricles causes the semilunar valves to close, which is the beginning of ventricular diastole. Note that the atrioventricular valves remain closed. When the pressure in the ventricles becomes lower than the pressure in the atrioventricular valves open and blood flows into the relaxed ventricles. This accounts for most of the ventricular filling. The atria then contract and complete the ventricular filling.
That's a pretty good explanation. Here's an animation on the mechanical events of the cardiac cycle. Okay, let's go to the next slide. The heart sounds. The heartbeat through a stethoscope sounds like lub, dup. The lub, the first heart sound, it occurs during ventricular systole. The AV valves are closing. The dup, the second heart sound, it occurs during ventricular diastole or relaxation when the pulmonary and aortic semilunar valves are closing. A murmur, or a normal heart sound from the cusp, not completely closing. Here's a slide of just where the mitral area sound would come from, or tricuspid area, aortic area, and pulmonary area. Cardiac muscle fibers form a functional syncytium. This is a mass of cells that function as a unit. Two such areas exist in the heart. In the atrial walls, it's called the atrial syncytium. In ventricular walls, it's called the ventricular syncytium. This next animation talks about the action potentials in the sino or SA node, sinoatrial node. Start with the potassium channels closing, then the sodium channel closes, and then the calcium channel opens. And then it closes, and so Sodium flows in again, and potassium flows out. This next slide illustrates the cardiac conduction system. Clumps are strands of specialized cardiac muscle which initiate and distribute impulses throughout the myocardium. The conduction system coordinates the events of the cardiac cycle. So we start at the SA node. The impulse is sent to the atrial syncytium, then to the junctional fibers, to the AV node and the AV bundle, and then is spread through the atrioventricular septum to the bundle branches, and from there to the Purkinje fibers and the ventricular syncytium. Here's an animation of the conducting system of the heart.
Action potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the intraventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
Another very good animation. This slide just illustrates a little bit exactly what the animation just told us, how the impulse travels to the junctional fibers, and then the AV bundle has a right and left branch, and those bundle branches spread to the ventricular through the septum to the ventricles, and then the Purkinje fibers spread everything through the muscle of the ventricles. In your text, 15.1 talks about replacing the heart from transplants to stem cell implants. Next, we'll talk about ECGs. An ECG is a recording of electrical changes that occur in the myocardium during the cardiac cycle. It's used to assess the heart's ability to conduct impulses. Deflections in a normal ECG or waves include a P wave, which is atrial depolarization, the QRS complex, which is actually 3 waves, that represents ventricular depolarization, and the T wave, which represents ventricular repolarization. Now we'll play an animation of the baroreceptor reflex control of blood pressure.
Increased blood pressure stretches the carotid arteries and aorta, causing the baroreceptors to increase their basal rate of action potential generation. Action potentials are conducted by the glossopharyngeal and vagus nerves to the cardioregulatory and vasomotor centers in the medulla oblongata. As a result of increased stimulation from the baroreceptors, the cardioregulatory center increases parasympathetic stimulation to the heart, which decreases the heart rate. Also, as a result of the increased stimulation from the baroreceptors, the cardiovascular center decreases sympathetic stimulation to the heart, which decreases heart rate and stroke volume. The vasomotor center decreases sympathetic stimulation to blood vessels, causing vasodilation. The vasodilation, along with the decreased heart rate and decreased stroke volume, bring the elevated blood pressure back toward normal. If the initial problem were a decrease in blood pressure, the activities and effects of the baroreceptors, cardiovascular center, and vasomotor center would be the opposite of what is illustrated.
So the parasympathetic would be decreased, while the sympathetic nerve impulses would be increased to increase blood pressure. The slide shows a little bit of the ECG pattern and what it represents. P wave represents atrial depolarization, and as the QRS takes place, the atria repolarize while the ventricles begin to depolarize, and this is full depolarization, section F, and then the ventricles begin to repolarize, and when they're fully repolarized, we see the T wave. And this shows different times. It starts with atrial systole and ventricular diastole, and we have a short period of that. And then we have the ventricular depolarization and the atrial repolarization, followed by the period of ventricular repolarization, and again we have atrial depolarization. And you see the pressure rises during ventricular depolarization and drops, while our atrial pressure rises slightly and drops to a flat level. And this talks about the ventricular volume. As it depolarizes, it then contracts, and the volume after ejection of the blood decreases. Then as we have repolarization, the volume increases. And this is one cardiac cycle in millivolts. 0 being the baseline, the P wave, the Q drops below 0, and then up to 1, and drops sharply again, and then flattens out again, and then elevates slightly at the T wave. And here's our heart sound: lub, AV valves closing, and DUP, the semilunar valves closing. The SA node controls the heart rate. There's also sympathetic and parasympathetic fibers that control the heart rate as well. There's also the regulatory reflex centers that were mentioned earlier that influence heart rate. Additional factors that can influence heart rate include physical exercise, the body temperature, and concentration of various ions, including potassium and calcium. But parasympathetic impulses will decrease heart action, and sympathetic impulses increase it. The cardiac center regulates the autonomic impulses to the heart. This slide shows a little bit of what happens. The receptor picks up a signal sent through a sensory or afferent neuron to the CNS. The message is integrated. It's then passed to a motor or efferent neuron to the effector muscle or gland. And that happens in the heart. The baroreceptors in the heart will send out the message. Here's the sensory fibers. They send a message to the medulla, and that message travels to the hypothalamus. Then there's the integration of the message, and the message is sent back to the parasympathetic vagus nerve and along to the SA node. And we also have sympathetic message that also can go to the heart if there's a need for the heart to increase. its stroke volume or contraction. Now we have an animation of action potential in cardiac muscle cells coming up. Again, it's going to be somewhat similar to what we saw in the last one. And it sodium channel opened. We had a pretty big spike in sodium. And then the calcium channel opened. And then the potassium channel opens. And we have a drop as the sodium channel closes. In your text, there's a clinical application on arrhythmias. It talks about different types of arrhythmias. Ventricular fibrillation is very rapid. It's an uncoordinated depolarization of the ventricles. Tachycardia is just a rapid heartbeat, while bradycardia is a slow heartbeat. An atrial flutter is an abnormally rapid state of atrial depolarization. So that P wave would spike instead of that rounded curve we have a big spike in the P wave. The slide talks about blood vessels. They're organs of the cardiovascular system. They form a closed circuit to and from the heart. They include the arteries that carry blood away from the ventricles of the heart, the arterioles that receive blood from the arteries and carry it to the capillaries. Capillaries where you have the site of exchange of substances between the blood and the body cells, especially the carbon dioxide and the oxygen. The venules receive this deoxygenated blood from the capillaries, and the veins carry that blood toward the atria of the heart. And here's a slide that shows the difference between arteries and veins. As you can see, the lumen in an artery, or the interior volume, is much bigger than an artery. Arteries are under higher pressure. Veins also, some of them have valves. The other layers, the tunica media is somewhat wider in the artery, and the externa and the endothelium are pretty much the same kind of tissue. Okay, don't know why this slide is up. We'll pass it up. Arteries and arterioles. The arteries have, like I said, have a thick, strong wall, 3 layers or tunics, have an endothelial lining, the middle layer of smooth muscle and elastic tissue, outer layer of connective tissue, and they carry blood under relatively high pressure, while the arterioles are thinner walls. They have an endothelial lining as well. The middle and outer layers are thinned. They have some smooth muscle tissue and a small amount of connective tissue, and they help control blood flow into a capillary. And here's an arteriole. Has a smooth muscle cell, forms a ring. There's a precapillary sphincter that opens up to send blood into the capillary. The capillaries are the smallest diameter blood vessels. They connect the smallest arteriole and the smallest venule. They're extensions of the inner linings of the arterioles, and the walls are just endothelium only, and they're semi-permeable. They have to allow for gas exchange. They show a meta-arteriole forming an arteriovenous shunt. They're showing the blood flow into the artery and into the arteriole and in the capillaries, and then we have this gas exchange going on, and then blood flows into the venule and then to the vein. This slide just shows a little bit of a capillary, and there's some slits in the capillary that allow for fluid to go out to the tissues. And here's another picture of the kind of the web that connects the arteriole to the venule. And this slide talks about the pressure outside and inside of a capillary. Blood flows from the arteriole. The outward force, including hydrostatic pressure, is 35 millimeters of mercury. And there's an inward force of osmotic pressure of only 24 millimeters of mercury. So that creates a net outward pressure of 11 millimeters of mercury. In the capillary, it's a little bit different. The inward force of osmotic pressure is higher, and the outward force is lower, so we have a net inward pressure of 8 millimeters of mercury. Venules are microscopic vessels that continue from the capillaries and merge to form veins. They have thinner walls than arterioles and less smooth muscle like elastic tissue than arterioles. Veins have thinner walls than arteries. The middle wall is poorly developed. Many have flap-like valves to carry blood under relatively low pressure. They function mostly as blood reservoirs. This illustration shows toward the heart, flaps opening, and this one back where the flaps close. Distribution of in the veins, systemic veins, large veins get some portion of the blood, but the small veins and venules get a smaller portion. Lungs get about 10%, the heart gets 8 to 11%, the arteries get 10 to 12% of blood, and the capillaries get 4 to 5% of blood. This table 15.3 just shows the type of wall they have and the function. In veins, they carry blood under relatively low pressure from a venule to the heart. The valves prevent a backflow of blood, which is good. Prevents edema in the legs. 15.5 talks about blood pressure, which is the force the blood exerts against the inner walls of the blood vessels. So it's pushing out the blood, push pressure on the walls. That blood pressure rises when the ventricles contract and falls when the ventricles relax. The systolic or top number is the maximum pressure during ventricular contraction, while the bottom number, diastolic, is the minimum pressure when the ventricles relax. This slide just shows some of the arteries, some of the more common arteries that you'll learn about. The temporal, the facial artery, carotid. The brachial artery, there's also a radial and an ulnar artery, and a femoral artery in the groin. Popliteal, down to the posterior tibial, and dorsalis pedis on top of the foot. Your book has a clinical application on blood vessel disorders, different types. Good picture of the development of atherosclerosis. You see an open lumen, and then plaque forms and lumen closes, and then figure C, it's just almost completely closed by plaque. Factors that influence arterial blood pressure. If blood volume increases, blood pressure increases. If heart rate increases, if stroke volume increases, blood pressure will also increase. Blood viscosity or thickness increases the blood. Peripheral resistance increases the blood. If you have poor circulation in your arms and legs, that's going to increase blood pressure, as it makes it harder for arterial blood to reach those places. (15.3) has a clinical application of the measurement of arterial blood pressure. Sphygmomanometer is used to measure it. That's a formal name for it. Most people today either have a electronic cuff that you can buy, a wrist cuff that just attached to your wrist, and push a button and boom, you get your blood pressure and heart rate usually. 15.4 has a clinical application on space medicine. Actually, I have a different one, so I'm not even going to talk about that. Okay, let's talk about controlling blood pressure. BP is determined by cardiac output and peripheral resistance. So BP equals cardiac output times peripheral resistance. Maintenance of blood pressure requires regulation of these two factors. So when you have an increased blood pressure, the heart responds by decreasing the heart rate and decreasing stroke volume, which decreases cardiac output. Or there can be decreased peripheral resistance and blood pressure is maintained. When you have decreased blood pressure, the increased heart rate and increased stroke volume will result in increased cardiac output, and there's also an increased peripheral resistance, and blood pressure will be maintained in that fashion. And here's a flow chart on it. So when the cardiac output increases, blood pressure rises, the baroreceptors in the aortic arch and carotid sinuses are stimulated. There's a sensory impulse sent to the cardiac center. The parasympathetic impulses to the heart are triggered, and they send a signal to the SA node and inhibit it, and the heart rate decreases. So then your blood pressure returns toward normal. When you have rising blood pressure, the stimulation of baroreceptors in the aortic arch and carotid sinuses occur. Sensory impulses are sent to the vasomotor center. The vasomotor center is inhibited. There's less frequent sympathetic impulses to arterial walls. There's vasodilation of the arterioles because of that, and decreased peripheral resistance, and blood pressure returns to normal. And here we go with the animation arteriolar resistance and blood pressure. And here's a venous return. Blood's pumped into the arteries. And we have a steady state of flow through the organs. And flow stopped. I think we just saw this one. It's called dilation compensation. Okay. Next slide talks about venous blood flow. Blood pressure decreases as the blood moves through the arterial system into the capillary network. So little pressure remains at the venular ends of the capillaries. It's only partly a direct result of heart action. It also depends on skeletal muscle contraction, your breathing, and venoconstriction. So you have relaxed skeletal muscle, which allows the veins to dilate more fully, and blood flows better to the heart. When we have contracted skeletal muscle, the valves close, and you have more blood pushing back to the heart because the valves open. Valves close at the bottom, but they open at the top and allow blood flow. The force of the contracted skeletal muscle pushes the blood forward and opens the valves. We have a clinical application on hypertension in the text. Actually, in my text, it's not about that. Central venous pressure. All veins except those returning to the heart from the lungs drain into the right atrium. This is therefore the pressure in the right atrium. Factors that influence it alter flow of blood into the right atrium. It affects pressure within the peripheral veins. A weakly beating heart will then increase central venous pressure. An increase in central venous pressure causes blood to back up into the peripheral veins. This can lead to peripheral edema. If blood can't get back into the heart because there's a backflow because the heart's not pumping properly, then blood backs up into the peripheral veins, and that leads to the edema. And there's another clinical application about exercise. And I'm not sure where that's at. I don't have it. Let's talk about the paths of circulation. We talked about the blood vessels can be divided into two major pathways, the pulmonary circuit and the systemic circuit, which includes the coronary circulation. And here's the pulmonary circuit. Again, we talked about this earlier. Blood coming through the superior vena cava into the right atrium, through the tricuspid valve, to the right ventricle, to the pulmonary semilunar valve. It goes left or right into the lungs, into the capillaries. There's gas exchange taking place. The oxygenated blood goes into the pulmonary veins, into the left atrium, through the mitral valve, into left ventricle, out through the aortic semilunar valve to the aortic arch, and then the aorta branches either ascending or descending. And here's a little bit about blood flow into the capillaries. There's a slight net outflow of fluid from the capillary. Solutes won't enter the alveoli but contribute to the osmotic pressure of the interstitial fluid. Any excess water in the alveolus is drawn out by the higher osmotic pressure of the interstitial fluid. Fluid from the interstitial space will enter the lymphatic capillary or the alveolar blood capillary. And we're showing how the lymph flow and the blood flow are parallel to each other. Systemic circuit is composed of vessels that lead from the heart to all body parts except the lungs and back to the heart. It includes the aorta and its branches, includes the system of veins that return blood to the right atrium. And 15.7 is a slide of the arterial system. All the arteries, starting way up at the top, you have the superficial temporal artery, the external internal carotid, the common carotid, the vertebral, the branches of the aorta. You see the subclavian, brachiocephalic, and the common carotid. There's a coronary artery. And then you have the descending aorta and then all the branches. And you have the common iliac, branches to the deep femoral and the femoral, and branch down into popliteal. Further branches, posterior tibial, fibular. And these are just principal branches of the aorta and the regions or organs they supply. For instance, the renal artery supplies the kidney. The phrenic artery supplies the diaphragm. The celiac supplies the organs of the upper digestive tract. And some other pictures. These are arteries with the veins, some of the veins, common carotid, internal, jugular overlapping. And here's a section on the abdominal aorta, and it's branching off. Superior mesenteric, inferior mesenteric. And here's an X-ray showing what it looks like. And then we have the arteries of the brain, head, and neck. And this portion here is called the circle of Willis. And it shows how the brachiocephalic, then there's the subclavian and common carotid here, and it runs up to the internal and external. The external towards the jawline, and the internal runs behind it and then disappears underneath the mandible. And these are the arteries of the shoulder and upper limb. You have the axillary, and we have the deep brachial and the brachial, and the radial, and the ulnar. And some of the arteries that supply the hand. And then here's the arteries of the thoracic and abdominal walls. You can see the thoracic aorta branches and runs through the costal cartilage. And the arteries of the pelvis and lower limb. And there's the blood supply to the testes. And you have the abdominal aorta that branches to the right and left common iliac. And here's the deep femoral and ephemeral. And then that there's a branch that comes off the lateral femoral, and the anterior tibial and fibullara, and a dorsalis pedis. And another slide of the venous system. The veins run almost in sync with the arterial structure. Characteristics of venous pathways. The vessels of the venous system originate with the merging of capillaries and venules, venules into small veins, and small veins into larger ones. Unlike the arterial pathways, however, those of the venous system are difficult to follow due to the irregularity of the networks and unnamed tributaries. And these are the veins from the brain, head, and neck. You can see the internal jugular, which everybody's probably heard of. There's also an external jugular. And the veins from the upper limb and shoulder. And then the veins from the abdominal and thoracic walls. And the veins from the abdominal viscera. Hepatic portal vein is very important. I'm going to see that and hear about that more about that. Here's another schematic of what happens in the deoxygenated blood in the veins and the oxygenated blood and where it goes. The blood, again, deoxygenated with low CO2 goes to the superior vena cava into the heart, and it goes to the lungs, and then it's oxygenated, heads back into the heart, and the aorta takes it to different branches, different arteries, and then in the capillaries you have the gas exchange, and that blood again taken, like the lower limb capillaries send blood to the common iliac vein, while the hepatic portal vein sends blood into the capillaries and out into the hepatic vein. And here we have the veins from the lower limb and pelvis. Great saphenous is a vein you might hear of, depending on what program you're going to be in. Last but not least, we have lifespan changes. The cholesterol deposits in blood vessels occur over time. The heart enlarges. It has to grow more muscle tissue as it gets weaker. The death of cardiac muscle cells also affect your system. There's an increase in fibrous connective tissue of the heart, an increase in adipose tissue of the heart, an increase in blood pressure, and a decrease in resting heart rate. And then 15.7 as molecular causes of cardiovascular diseases. You're going to have a connective tissue defect in Marfan syndrome. A normal form of connective tissue protein called bilirubin weakens the aorta wall, dilating the aortic root, and so that the weakened aorta can cause sudden death. And the next clinical application is on coronary artery disease, and then different causes of it and different treatments for it. Okay, let's talk about the outcomes that are going to be assessed for this chapter. So we need to be able to discuss the functions of the organs of the cardiovascular system, including the heart and the blood vessels. You need to understand the structure of the heart, distinguish between the various coverings of the heart and the layers that compose the wall of the heart. The epicardium, the myocardium, and the endocardium. You should be able to identify and locate the major parts of the heart and discuss the function of each part, and be able to trace the pathway of the blood through the heart and the vessels of the coronary circulation. Also, should be able to describe the cardiac cycle and explain how heart sounds are produced, the ventricular depolarization and ventricular repolarization. Identify the parts of a normal ECG pattern and discuss the significance of this pattern. What does the P wave represent? What does the QRS complex represent? What does the T wave represent? Explain how the cardiac cycle is controlled. Compare the structures and functions of the major types of blood vessels. Describe how substances are exchanged between blood and capillaries and the tissue fluid surrounding body cells. Explain how blood pressure is produced and controlled. Describe the mechanisms that aid in returning venous blood to the heart. Compare the pulmonary and systemic circuits of the cardiovascular system. Identify and locate the major arteries and veins, and describe the lifespan changes in the cardiovascular system. Well, that is the end of our PowerPoint slideshow for today on Chapter 15. Monday at 4:30, I will be discussing Chapter 16, the lymphatic system and immunity. And at 4:30 p.m. Monday, we will July 21st, we will be offering that PowerPoint presentation. I hope you had an interesting experience watching this. It was one of our very first ones that was successful, and I hope to see you again Monday. Good night, and have a great weekend.